Hello, everyone, and welcome to the Ben's Chem Videos Sunday night live stream. Tonight, we are going to continue our discussion on thermodynamics that we started a week ago. That's right, last week we introduced a brand new topic, thermodynamics. It was like this nice, short, introductory live stream, and tonight we're going to get a little bit deeper into the knowledge. So without further ado, I present to you Thermodynamics Volume 2. As always, your feedback is more than welcome and highly appreciated, so please feel free to drop your thoughts in the chat if you're watching this live, and if you're watching this as a video, please feel free to leave me a comment, because without your feedback, I am completely and totally lost. I would also like to add that by the time I'm done processing and trimming and editing this live stream, there will be a playlist called Thermodynamics Live Streams, where you can find Volume 1, Volume 2, and indeed the rest of the volumes, however many volumes it takes, to complete this topic of thermodynamics. All right, so we're going to kick things off just by briefly reviewing the content from a week ago. That was Volume 1. It looks like I already have a message in the chat from Goose. Goose says hello. Hello, Goose. Thank you very, very much for being in here. Welcome back. Appreciate it. And he also sent a super chat or a sticker. Oh, yeah, that is a super chat. Thank you for your support, man. I wholeheartedly appreciate that, and I would encourage anybody to support the stream if you find the content valuable. Thank you very much. All right, so let's review the content briefly from Volume 1. So the first thing that we did last week was to simply ask the question, why? Why do physical and chemical changes occur in the first place? And that led us directly into the definition of spontaneous and non-spontaneous processes. Spontaneous process, of course, being one that occurs without ongoing outside intervention, and a non-spontaneous process cannot occur without ongoing outside intervention. And we talked about simple mechanical systems and how for simple mechanical systems, such as holding an apple up and then letting it go and the apple spontaneously falls down, those are relatively easy to predict. It's easy to predict the direction of spontaneity of a simple mechanical system where you have like gravitational potential energy or something like that. But for chemical systems, it's not very obvious, right? And the example that I went over from last week was like the Statue of Liberty, right? When it was first built, it was this bronzy copper color, and then over time, it underwent oxidation to become this green color that it is today. And that happened spontaneously, but why? Like, what's the driving force behind the Statue of Liberty turning from the copper color into green, right? In other words, what we're looking for is something called a chemical potential, a thermodynamic property that predicts the direction of spontaneous chemical change, right? And so in our search for a chemical potential, it's important that we understand a few things about thermodynamics already. I assume you guys have already learned about thermochemistry. If you haven't, or if you are not super confident in your understanding of thermochemistry, fear not, because I do have an entire playlist about thermochemistry where we talked about things like the first law of thermodynamics and enthalpy. So we had to sort of dig back into our memory banks and revisit those topics. So the first law of thermodynamics basically just says the total energy of the universe is constant. Energy is neither created nor destroyed in any chemical process, right? And that's important to understand. And also, we looked at enthalpy, right? We revisited the topic of enthalpy, which of course is the sum of the internal energy of a system and the product of its pressure and volume, and it equates to the amount of heat absorbed or released by a system under conditions of constant pressure. So if you don't understand enthalpy very well, again, I do have a video on that. All of that stuff is in my thermochemistry playlist. And so we looked at enthalpy as kind of like a candidate for a chemical potential, right? If we're searching for a chemical potential, the first candidate in our search might be enthalpy. However, if enthalpy was a chemical potential, if enthalpy was a thermodynamic property that predicts the direction of spontaneous chemical change, then we would expect all exothermic processes, all processes that release heat under conditions of constant pressure, to be spontaneous, and all endothermic processes to be non-spontaneous, which is actually not the case. There are several endothermic processes that do occur spontaneously, such as the melting of ice at temperatures above 0 degrees Celsius, the evaporation of liquid water into water vapor, the dissolution of sodium chloride into sodium and chloride ions to form an aqueous solution of sodium chloride. All of those are endothermic processes. They absorb heat from their surroundings, and yet they occur spontaneously. And so enthalpy cannot be a chemical potential. It cannot be a thermodynamic property that predicts the direction of spontaneous chemical change. But if you think about it, right, water, ice melting, right? Ice melting, water evaporating, sodium chloride dissolving into ions. What do those three processes have in common? Well, what they have in common is an increase in randomness, an increase in disorder. In all three of those processes, those samples start out in a more orderly configuration and become more disorderly. And that leads us into entropy. And again, entropy, not to be confused with enthalpy, right? Entropy is that thermodynamic function that increases with the number of energetically equivalent ways to arrange the components of a particular system. And just plain English way of defining entropy would be a measure of disorder or randomness. So entropy is a chemical potential. Entropy is what drives spontaneous chemical change. It's all related to the amount of disorder, the amount of randomness in the universe. And so there's a couple of equations that we looked at over here, like this one, S is equal to K ln W. So S, of course, that's the entropy. K, that's the Boltzmann constant, and W is the number of energetically equivalent ways to arrange the components of a sample. So this is kind of the first equation that we looked at. This equation is actually engraved on Boltzmann's tombstone, so pretty serious stuff, right? And then, of course, we also understand that entropy is a state function, right? State function, what does that mean? It means that the value of entropy, or the value of any state function, depends only upon the state in which it is at that particular time. It does not depend on how the system arrived at that state. And that would be called a path function. So things like heat and work, those are path functions. They do depend on the path taken to arrive at a particular state. State functions like enthalpy and like entropy do not depend on the path taken. So that's kind of all the stuff that we talked about from volume 1. So anything that tends toward an increase in randomness, energy dispersal, randomization, those would lead to an increase in entropy, and so they would occur spontaneously. So let's talk about entropy as it relates to changes in the state of matter of a particular sample. So if you have a sample of matter and it undergoes a phase change, let's say it's a solid and it melts into a liquid, or let's say it's a gas and it condenses into a liquid, right? What would be the entropy, the sign of the entropy change associated with those changes in state of matter? So to do this, what I'm going to do is I'm just going to hop over to the whiteboard and we can sort of intuitively figure this out, right? So let me do it on my screen here. Right now, my PowerPoint is still up. Where's my whiteboard? Okay, there it is. Okay, so here we have the three states of matter: solid, liquid, gas, and we have all of the phase changes that occur between those states: melting, freezing, vaporization, condensation, sublimation, and deposition. So let's see if we can figure out whether entropy would increase or decrease during all of these phase changes. So let's start with melting, right? A solid melts into a liquid. So what happens when a solid melts into a liquid, right? You have a configuration, a highly ordered configuration of those molecules. And then when it melts into a liquid, you have a much more disorderly arrangement of molecules. So if a solid is melting into a liquid, you're going from an orderly to a more disorderly state. That means that your entropy would increase, right? So that means that delta S, the change in entropy, would be positive for that sample of matter, right? Entropy increases going from something that's orderly to something that's disorderly, right? By contrast, let's say you go in the other direction where you have a liquid and it freezes into a solid. Well, now you're going the other way, right? You had something that was relatively disorderly becoming something that is much more orderly, and so that would be a decrease in entropy. So that means that your delta S, your change in entropy, would be negative. It would be less than 0 in the case of freezing, right? Let's look at phase changes between liquid and gas, right? Let's talk about liquid vaporizing into a gas. Well, you have a fairly disorderly sample of molecules in the liquid phase, but then when they vaporize, they become much, much more disorderly, right? More randomization, more dispersal of energy, more places to put energy, if you will. So vaporization, therefore, would be something in which your delta S, your change in entropy, would be positive, right? And for condensation, right, what do you have? You have a gas, something that's very, very disorderly, condensing down into a liquid, which is much more orderly. Condensation would be a situation in which delta S would be negative. It would be less than 0. And finally, if we look at sublimation and deposition, so you can probably already figure this out, but I think it's probably worth our time to go through them anyway, right? If you have sublimation, solid going directly into the gas phase, that's something that's very, very orderly, becoming something that is very, very disorderly, something that is way more random. And so sublimation would be a situation in which your change in entropy would be positive or greater than 0. And then finally, for deposition, a gas becoming a solid, something disorderly becoming something highly orderly, that would represent a situation in which your entropy change is negative, less than 0. So your entropy change will be positive. Entropy will increase whenever you are going from an orderly to a more disorderly state. Entropy change will be negative. Entropy will decrease whenever you're going from something that is disorderly to something that is more orderly, right? So I hope we are all on the same page about entropy changes with regard to changes in state of matter, and I would really, really hope that if we weren't, that you would let me know, because I need your feedback, right? Yeah, still need your feedback. Always need your feedback. All right, so let's go back to the PowerPoint real quick. I just wanted to also highlight gas phase reactions real quick. So let's say you have a gas phase reaction. You have a chemical reaction in which all of the reactants and products are gases, such as this equation right here. This balanced chemical equation describes the combustion of butane, which is that reaction right there, right? It's a butane lighter, so the combustion of butane. I'm trying to make these streams more relevant to daily life, so see that flame right there? Yeah, that's this reaction. That reaction is described by this chemical equation right here. Anyway, if you have a gas phase reaction such as this, right, what happens to the entropy? Does it decrease or does it increase? Well, it depends on the number of moles of gas on either side of the equation, right? So if we count the number of moles of gas in this balanced chemical equation, we can clearly see that on the left-hand side of the equation, the reactants, we have 15 moles of gas, right? We have 13 from that oxygen, plus another 2 coming from that butane, that C4H10, right? But then if you look over on the product side of the equation, the right-hand side of the equation, we've got 18 moles of gas total, right? 8 from that CO2 and 10 coming from the water, right? So the rule of thumb here is that entropy increases when the number of moles of gas increases, right? So if you're going from fewer moles of gas to more moles of gas, as we are in this case for the combustion of butane here, then the sign of delta S would be positive. Entropy would increase in this situation for this particular reaction. So we're going to do just a couple of little examples of sort of predicting the sign of delta S for a couple of different changes here. So this problem is asking us to predict the sign of delta S for each of the following processes. First process is dry ice subliming. Second process is gaseous water becoming, or gaseous oxygen rather, becoming liquid oxygen. And the third process is this chemical reaction here where we have 2 NaCl yields 2 NO and Cl2. So what do you guys think would be the sign of delta S for each of these processes? And that's not a rhetorical question. I would really, really like your participation here as I copy and paste this into the whiteboard. Give me a second to do all that. So think about it and see what you can come up with. And remember, the only dumb question is one that is never asked. You know what? I just have to admit, I don't really believe that. There's a lot of dumb questions out there. But don't let that deter you from typing your thoughts in the chat. Let me know what you think about this problem. So let me go ahead and paste it in the whiteboard real quick, and I'll go ahead and take you guys to the whiteboard right along here with me. So here we go. Let me enlarge it real quick so we can all see. Oh, it's kind of big. Let's see. That looks pretty good. Okay, I guess I can put it down here. Yeah. Okay, so we're going to predict the sign of the entropy change, delta S, for each of these processes, starting with the first one, dry ice subliming. Well, what is dry ice? Dry ice is solid carbon dioxide. And if it sublimes, that means it's undergoing sublimation to become gaseous carbon dioxide, right? Now, if something's a solid and it turns into a gas, that means it's something that was very orderly becoming something that is very disorderly, right? And if something is becoming more disorderly, that means that entropy would increase, right? And so delta S would be positive in this case, right? More dispersal, more randomization, more disorder occurring. That always means an increase in entropy. Second one, it looks like we already have some answers from Goose. Thank you for your super chat, by the way, Goose. I am very, very grateful for your support. Thank you, guys. Thank you. Thank you, Goose, and thank you to anybody who is also considering sending a super chat. I would wholeheartedly appreciate that. All right, so the second example, we've got O2 gas becoming O2 liquid. Well, in that situation, what happens? Well, we have a gas, which is highly disorderly, right? Something that has an indefinite shape and volume, becoming a liquid, which is fairly disorderly, but not nearly as disorderly as a gas, right? Something that has a definite volume, but an indefinite shape, right? So it's decreasing in randomness. And if it's decreasing in randomness, that means it's decreasing in entropy. So for the second one, delta S would be negative. It would be less than 0, right? Because it's becoming more orderly. Third one, right? We have this gas phase reaction here. And so with gas phase reactions, as we just saw a moment ago, it's all about the number of moles of gas. How many moles of gas do we have on the left-hand side versus the right-hand side? Looks like we have 2 moles of gas over here on the left-hand side, and then we have 2 here plus the understood 1 there, or 3 moles. I'll just put that in this purple color. So we have 2 moles of gas on the left-hand side. We have 3 moles of gas on the right-hand side. And so if the number of moles of gas increases for a gas phase reaction, that means you are going to have an increase in entropy. And so therefore delta S would be greater than 0. It would be positive in this case. So I hope we're all on the same page with that, because we are going to be moving on. Things are going to get a little bit deeper, a little bit hairier as we go forward. So let's go back to the PowerPoint real quick, and we will continue this discussion. By the way, if you haven't already done so, I would wholeheartedly appreciate your leaving a like on this video, on this stream. It actually does quite a bit to help with discoverability. And if you see my numbers, I definitely need help with that. So, all right, let us continue. Okay, so now we are at the point, I think, where we've talked enough about spontaneity and entropy to formally define the second law of thermodynamics. So here it is. Second law of thermodynamics says that for a spontaneous process, the entropy of the universe increases, right? And entropy of the universe, we give that a symbol of delta S, and then this UNIV subscript underneath is greater than 0. For any spontaneous process, the entropy of the universe increases. The level of disorder, the level of randomness, the level of energy dispersal of the universe increases, right? Now, it's important to understand that when we talk about thermochemistry or thermodynamics, we define the universe as being composed of 2 components, which are the system, abbreviated SYS, and the surroundings, which is abbreviated SURR. And so we get this equation down here where we have delta S for the universe is equal to delta S for the system plus delta S for the surroundings. Very, very important to understand that. So when you have a thermodynamic system, that's the part of the universe that you are focusing on. That's the part that you're studying. And the surroundings is literally everything else in the universe. Delta S universe is equal to delta S system plus delta S surroundings. Okay, so now that we understand that, I think we're ready to move forward even more. So you might be thinking to yourself, well, there are some situations that occur spontaneously, but it seems like, according to the second law, entropy is actually decreasing. So imagine a frozen lake. So this is some location in which the weather is very, very cold, certainly lower than 0 degrees Celsius. And we have a lake, we have a body of water that has spontaneously frozen. How is that possible, right? Why would it freeze? Why would it go from a disorderly arrangement of liquid water molecules to an orderly arrangement of solid water molecules, right? Doesn't that mean that entropy is decreasing? Why would this happen spontaneously if entropy seems to be decreasing? Well, it's important to remember that the criteria for spontaneity is the entropy of the universe, not the entropy of the system. So if we consider the lake to be our system, right, the equation breaks down like this, where we have delta S for the universe is equal to delta S for the system plus delta S for the surroundings, right? Now we know that delta S for the system would be negative if the system is the lake, because again, the water is going from liquid, which is disorderly, to solid, which is much more orderly, right? So we know that delta S for the system would be negative, but in order for this process to be spontaneous, which it is, the entropy change for the surroundings must be positive. And not only must it be positive, but delta S for your surroundings must be positive and larger in magnitude. In other words, the absolute value of it is larger than the absolute value of delta S system for this delta S universe term to end up being positive, right? So this is why this occurs spontaneously. It's because even though our entropy of our system is negative, the entropy of our surroundings is positive somehow. And it's also positive so much that it can overcome the negativeness of the entropy change of this system, right? So that's when you have a frozen lake. Now imagine that you're in a much more warmer climate, right? And you have a body of water here at this nice looking beach right here. And this water hasn't frozen at all, right? It has remained liquid. So what's going on here? Well, in this case, again, the entropy change for the universe is just the sum of the entropy change for the system and the entropy change for the surroundings, right? The entropy change for the system for water freezing, as we established earlier, is negative, right? Now, the entropy change for the surroundings, that would be positive, but it would, in this case, it would be smaller in magnitude than the entropy change for the system, right? So we've seen here that the delta S for the surroundings is temperature dependent, right? If it's cold, then it has a large magnitude. If it's hot or warm, then it has a small value. It has a small magnitude. So what is going on here, right? What is going on? So let's see if I can, trying to think of which screen I should go to sort of explain this. So, wow, I'm just totally blanking right now, guys. I apologize. Okay, so I'll just go back to this screen so that I can explain this real quick. So we understand that the entropy change for the surroundings seems to depend on temperature. And the reason why is because, again, if you think about the process of water freezing, right? The process of water freezing to become ice is actually exothermic. It actually releases heat into the surroundings. And anything that releases heat into the surroundings is going to have an effect upon the entropy of the surroundings. Because if you're giving the surroundings heat, you're basically giving the surroundings more energy dispersal. So you're increasing the energy, or the entropy rather, of the surroundings when you have something that is exothermic, right? But it also depends on temperature, right? If you add heat to something that is already hot, then it's not going to have a very profound effect. If you add heat to something that is cold, then it is going to have a profound effect. So imagine, let's use an analogy here. So imagine that you give a random person $5,000, right? That would be a very, very charitable thing to do, right? Now, if you give that $5,000 to a very poor man, that's going to make a profound impact because he doesn't have any money, or he has very, very little money. If you give $5,000 to a very rich man, well, it doesn't really have much of an effect on him because it has so much money. That's kind of how it is with these exothermic processes and how they influence the entropy change for the surroundings, right? If you have a very, very cold temperature, then adding a little bit of heat to the surroundings is going to result in a very, very large entropy change for the surroundings. And if you add a little bit of heat to an environment where the temperature is already high, then that's not going to have much of an effect on the entropy change for the surroundings. So this kind of explains why at cold temperatures, water freezes spontaneously, and at hot temperatures, water does not freeze spontaneously, because it's all about the entropy change of the surroundings and the effect that the exothermicity, right, the tendency of water to release heat into the surroundings when it freezes, what effect that has on that entropy change of the surroundings. Now, let me go to the whiteboard real quick because I wanted to do a little derivation here, which is going to allow us to understand and to sort of quantify the changes in entropy for the surroundings, right? So we're talking about delta S for the surroundings. And let me move that a little bit closer so you guys can see it. What's going on here? I don't know why I'm off the screen there. Oh, this stream is just going so well, you guys. Okay, there we go. So this delta S surroundings term, we are in a position where we want to sort of understand this better and we can quantify it. Now that might seem like a daunting task, right? Because how do you quantify the entropy change for the surroundings when the surroundings is like literally everything else in the universe? That can seem like a very, very difficult thing to do. But it turns out we can actually quantify the entropy change for the surroundings by understanding a few things about the enthalpy of the system, right? So we know at this point that if something is exothermic, it will have an effect upon the entropy change of the surroundings, right? So in other words, we can sort of write that out as a proportionality, right? So we can write out that the entropy change, the delta S for the surroundings, is proportional to, so this symbol over here means is proportional to the negative of the amount of heat that is given off by the system. So this ΔHsys here, that is heat, right? So it's all about heat transfer, right? If you add heat to the surroundings, you're going to increase the entropy change of the surroundings, right? So whatever heat is lost by the system, that is the proportional to the entropy that is gained by the surroundings. And so we arrive at this proportionality here. And a moment ago, we also established that the entropy change of the surroundings is inversely proportional to the temperature, right? So that leads us to this proportionality here where we have delta S surroundings is proportional to 1 over the temperature, right? And that kind of explains, again, why water spontaneously freezes at cold temperatures, but it doesn't spontaneously freeze at warm temperatures, right? Because if you add heat to something that's already hot, you're not having much of an effect on the entropy. If you add heat to something cold, then you are having a profound effect on the entropy of those surroundings, right? So we can combine these proportionalities into an equation. And the equation would look something like this, where we have delta S. I just realized I didn't put the S there. Okay. So we can combine these into equations where we have delta S is equal to negative Q for the system, right, divided by the temperature, right? Now let's assume for the moment, because assuming this allows us to, how should I say this? If we make the assumption that we have a constant pressure, right? Constant pressure and constant temperature, right? This whole delta S for the surroundings is equal to delta or minus Q for the system divided by T. That only works at constant temperature, right? So if we assume that our pressure is constant in addition to our temperature, well, we know, or at least we should know, that under conditions of constant pressure, delta H is equal to Q, right? And so delta H for a system is going to be equal to the heat absorbed or released by that system under conditions of constant pressure. This is also true, right? So that means that we can substitute this negative ΔSys term, and we can substitute that for negative delta H for the system, right? And so we arrive at this equation here, in which the entropy change for our surroundings is equal to the negative of the enthalpy change for the system divided by the temperature. Now, it's important to understand two things about this equation. The first thing that's important to understand is that this only works if your pressure and your temperature are constant. Otherwise, this equation, well, it's not meaningless, but it just won't work. And the other thing to remember is that the temperature must be reported in kelvins, right? This has to be reported in kelvins. So if you're given a Fahrenheit temperature or a degree Celsius temperature, you must convert that into kelvins in order for it to be compatible with this equation here. So this is actually a very, very powerful position for us to be in, because we can quantify the entropy change for the surroundings just with knowledge that we have about the system and the temperature under which that system is, right? So the last thing that we're going to do in this stream is we're just going to do a multi-part problem in which we get to sort of think about this a little bit more deeply. We get to apply this equation here, and then we will be done for the night. All right, so let's go back to the PowerPoint. Let me just kind of get situated here. So at the PowerPoint. Okay, so here's the problem, right? So this is the same chemical equation that we saw before, right? The combustion of butane, this one right here, right? It's the same equation. So first part of the problem says to calculate the change in entropy in the surroundings at a temperature of 25 degrees Celsius. Second part says determine whether the change in entropy for this system is positive or negative. And then third, it simply asks us, is this reaction spontaneous? Very, very good questions, right? So let me go ahead and copy and paste this into the whiteboard, and then we can sort of take a stab at solving it. So let me select all, and then we'll go over to the whiteboard, and gonna get rid of all that stuff. Where are you? And okay, just gonna resize this. Okay, I'm gonna resize myself too. I'm gonna make myself a little bit smaller so that we can all read what's going on. All right, so first part of the question says to calculate the change in entropy of the surroundings at a temperature of 25 C, right? So earlier we sort of derived the equation for how to do this, right? So we know that the delta S for the surroundings is equal to negative delta H for your system divided by T, right? And so all we need to do is to simply find the enthalpy change for this reaction. It's something that you can find tabulated in your chemistry textbook. Unfortunately, I forgot to provide it in the problem, so you really need that information in order to solve this, so I'm going to have to look that up. So we have negative of the delta H of the system, whatever that happens to be, divided by the temperature, right? So the temperature, of course, that's the temperature, temperature's given in degrees Celsius, 25 degrees C. We have to convert that into kelvins, and as we should all know, the Kelvin temperature is going to be equal to the degree Celsius temperature plus 273.15 kelvins, right? The Kelvin and Celsius scales are basically the same scale in that the size of a degree is the same between the two. It's just one scale is sort of shifted 273.5 degrees, 0.15 degrees away from the other. Got a message from Kaylee, says, hello, just dropping by to see how you're doing. I am doing very, very well. Thank you so much for stopping by and dropping me a line, and I hope you're doing well also. I hope you and your entire family, plus the one, are doing very, very well. All right, so we have our formula here to convert from Kelvin, or from degrees Celsius to Kelvin, right? So if we just simply put that 25 degrees Celsius, right, 25 degrees Celsius, we're going to add 273.15 to that in order to get our Kelvin temperature. So that would be, I'll just round it to the ones place here. That would be 298 kelvins, right? 25 plus 273 is 298 kelvins. And if you'll bear with me for just a moment, I'm just going to find out the delta H value, the enthalpy change for the combustion of butane here. Let's see. I'm just Googling it right now. So combustion of butane, delta H. Okay, according to Google, it is 2,877.5, and that's kilojoules per mole, right? 2,877.5 kilojoules per mole. And again, this is just something that I looked up, right? This is something that you'll either be given in a problem or you'll be expected to find it in your chemistry textbook somewhere, right? It's the delta H for this system for the combustion of butane here, right? And so if we perform this calculation here, which again, I have not yet done, I'm going to go ahead and do that. And by the way, I would encourage anybody, if we're doing a problem, to bring your scientific calculator with you so that you can follow along. That would be cool, because sometimes I make mistakes, and, you know, I'm human after all. So, okay. So let's plug this into our calculator. So we have negative 2877.5 divided by 298. And that gives us, negative, I'll just do it to 3 sig figs here, negative 9.66. And it looks like I am off the screen again. Let me fix that. So we have negative 9.66, and that's kilojoules per Kelvin. Now, the usual unit of entropy is joules per Kelvin, so if we wanted to convert this into joules per Kelvin, we could easily do so by multiplying this negative 9.66 by 1,000. But you get the idea here. All we were doing is we were just applying this formula here, in which we have the entropy change for the surroundings is equal to negative enthalpy change for the system divided by the temperature in kelvins. And again, this only works when you have conditions of not only constant temperature, but also constant pressure. If you don't, then this equation won't work, right? So we calculated that. So I'm just going to write this in. I'm just going to squeeze it in up here. Negative 9.66 kilojoules per Kelvin, right? All right, so now what I'm going to do is I'm just going to erase all this stuff here, and we will get started with the second part of this problem here. So number 2 is telling us to determine whether the change in entropy for this system is positive or negative. You know what? I'm not sure if I did that right, to be honest with you. Did I get that right? No, I did it wrong. I'm sorry, guys. Okay, I did that wrong. I'm glad I caught myself, because I didn't want to give you guys wrong information. So let me just go back and see if I can go back. All right, so this is the problem that we worked out. What I just literally now messed up on was this right here. So when I looked up the combustion of butane, the delta H for that, what I didn't take into account, and I should have noticed this, is that the delta H for that is actually negative. So instead of 2,877.5 kilojoules per mole, it's actually negative 2,877.5 kilojoules per mole, right? So what that means is that we need to flip the sign here. So instead of negative 9.66 kilojoules per Kelvin, it's positive 9.66 kilojoules per Kelvin. Sorry about that, because if we multiply a negative by a negative here, then it becomes a positive. So that's something that I missed. I apologize, and I think we are ready to move on. Okay, and I guess I should also include the mole down here, because it was kilojoules per mole divided by Kelvin. So in this case, it would be kilojoules per Kelvin per mole. I hope I haven't lost everybody, because we're going to move on. So number 2 says to determine whether the change in entropy for the system is positive or negative. Now, actually, this is kind of something that we did earlier, right? When we were talking about gas phase reactions, it's pretty straightforward. If you have if you're going from fewer to more moles of gas, then the entropy will increase, delta S will be positive. And if you're going from more moles of gas to fewer moles of gas, then your entropy change will be negative. So it looks like we have, and again, this is all stuff we did before, but we have 15 moles of gas on the left-hand side of the equation, right? 13 from the O2 plus the additional 2 from that butane. And then we have 18 moles of gas over here on the products, 10 from the water, 8 from the CO2. And since we're going from fewer to more moles of gas, that's more energy randomization, more energy dispersal, more disorder, more randomness. All of that points to an increase in entropy. So that means that this will be a positive, right? It'll be a positive delta S. The other way to write that would be that delta S for your system is going to be greater than 0. And then the final question is the reaction spontaneous, right? Is the reaction spontaneous? Well, what's the criterion for spontaneity? The criterion for spontaneity is that the entropy of the universe increases, right? Is there any way to tell knowing what we know about this reaction occurring at this temperature, whether the entropy of the universe will be positive? Well, let's take a look at the formula, right? So delta S for the universe, UNIV, is equal to delta S for your system. And I didn't do a good job on that. Let me try that again. Delta S for your system plus delta S for your surroundings, right? Now, in this case, delta S for our surroundings, that's the positive 9.66 kilojoules, right? And we also know that the delta S for the system, because of the fact that the moles of gas increase over the course of this reaction, we know that the delta S for the system is positive. So since delta S system is positive and delta S surroundings is also positive, then that means that delta S universe must also be positive. There's no way to combine two positive numbers and somehow end up with a negative number, right? And so since delta S for the universe has to be positive, right, we can confirm that this reaction will be spontaneous according to the second law of thermodynamics, which I will remind you states that for any spontaneous process, the entropy of the universe increases. Delta S is positive. All right, everybody. So that is just about gonna do it for me tonight. Thank you very much for joining me. I sincerely hope that you found the stream valuable, and I hope I didn't lose you anywhere. I know there were some parts where I kind of got a little tongue-tied a little bit, maybe a little stage fright. I'm actually a pretty introverted person, so doing these live streams is actually not very comfortable. It doesn't come very natural to me, so I'm trying to get over that. But anyway, I hope this stream was valuable to you, and stay tuned because next Sunday, I believe, I don't know, next Sunday might be weird because it's Thanksgiving and I'm going to be out of town, so I'm not sure when I'm going to come back to my home to be able to do a live stream. So I would like to do volume 3 next Sunday, the 28th, but I'm not sure if I'm actually going to be able to because I haven't really ironed out all of my travel plans for the weekend. To that end, though, I hope you guys have had a great weekend. I hope you will have a wonderful week this week. I know a lot of folks in the United States, like me, you have Thanksgiving off, you have Friday after Thanksgiving off. So even though it's a short week for many of us, I hope it's a very, very nice, very safe, very fun, very productive, very awesome week for you guys. So, all right, that does it. And yeah, I always stream Sunday nights, 9 o'clock p.m. Eastern Standard Time. So I would love to see you in the next stream. And all right, that's it. Take care.